This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to this discussion. Today we're delving into a research paper that examines the robustness of deep neural networks, DNNs, specifically focusing on semantic segmentation in the context of embedded systems. The paper investigates the impact of single-event upsets, SCUS, on the performance of these networks. What are the key challenges in ensuring the reliability of DNNs in embedded systems, particularly those used in safety-critical applications?
The primary challenge lies in the inherent vulnerability of DNNs to soft errors caused by SEF. These errors, often single-bit upsets, SBUS, can corrupt the DNN's parameters, weights, and biases, leading to unpredictable and potentially catastrophic consequences in safety-critical applications like autonomous driving or aerospace. The problem is exacerbated by the trend towards deploying increasingly complex DNNs in resource-constrained embedded systems.
The paper mentions model compression techniques like pruning and quantization as ways to address resource constraints. How do these techniques affect the DNN's susceptibility to SEUs?
That's a crucial point. While pruning and quantization reduce model size and computational complexity, they can also inadvertently increase vulnerability to SEUs. Pruning removes less important parameters, potentially leaving the network more sensitive to errors in the remaining parameters. Quantization reduces the precision of the parameters, making them more susceptible to bit flips. The paper investigates this trade-off between resource efficiency and robustness.
The paper conducts a layer-by-layer and bit-by-bit sensitivity analysis. What were the key findings of this analysis regarding the impact of SBUS on different model parameters?
The analysis revealed that the sensitivity to SBUS varies significantly depending on the parameter type, its location within the network, and its bit position. Batch normalization, the layers in particular, proved highly sensitive due to the nature of their calculations. Bit flips in the exponent bits of floating point parameters often had a more significant impact than those in the mantissa. The paper also found that the sensitivity differed between encoder and decoder layers in the UNet architecture.
The paper explores both 32-bit floating point and 8-bit quantized representations. What were the differences in robustness observed between these two representations?
The 8-bit quantized models, QNNs, generally exhibited greater robustness to SBUS than their 32-bit floating point counterparts. This is because the two's complement representation used for integers doesn't have special values like NaN or infinity, which can cause unpredictable behavior in floating point models when bits are flipped. However, the sensitivity to bit flips in the sign bit of the quantized biases was still significant.
The paper also investigates the impact of multiple bit upsets, MBOS. What insights did this analysis provide?
The MBU analysis showed that the unpruned quantized model was significantly more robust to random MBUS than the pruned quantized model. This highlights the trade-off between model size and robustness. The unpruned model, despite its larger size, could tolerate more errors before significant performance deprivation. The study also provides estimates of the expected number of SEOF per hour for both models based on industry fit rates.
The paper proposes several lightweight error mitigation techniques. Can you summarize these techniques and their advantages?
The paper proposes a method to modify the model's parameterization to prevent risky states where a single bit flip could lead to a significant change in the parameter's value. This involves identifying parameters with exponents close to being fully filled and slightly adjusting them to reduce their sensitivity. The method introduces no memory or computational overhead. Additionally, the paper suggests other techniques like sparse pruning and redefining batch normalization parameters to further enhance robustness without additional costs.
What are the limitations of this study, and what are potential avenues for future research?
The study focuses on a specific model architecture, UNet and dataset, HSI Drive v2.0. Further research should investigate the generalizability of the findings to other architectures and datasets. Exploring more sophisticated error mitigation techniques, potentially incorporating hardware-level solutions, is also warranted. Finally, a deeper investigation into the impact of different quantization schemes and pruning strategies on robustness would be valuable.
This has been a very insightful discussion. Thank you for sharing your expertise on this important topic.